Okay, welcome everyone to the morning session. Just a couple of quick announcements about the mini courses. So one thing is the schedule of the mini courses has changed slightly. From Wednesday onwards, they've swapped. So check the program, please, before you go to the mini courses. So on Wednesday morning, it's me, not Alex, most importantly. Second thing about my mini course is that, so from today, it will be slightly faster. So people who have seen a little bit of the probabilistic method, but not a lot, are welcome today, okay? Sorry, I'll pass to Marcel to talk about the talent show.
Okay, so on Thursday we're having a talent show from 4 to 8 in the Churrasqueira. And if you have talents, you should come to me and say you have a talent so I can get the talents in. Yeah, last time we had like a lot of good talents, like musical talents and other kinds like juggling, I don't know, like characters, contortionism, all kinds of things. And okay, if you don't find me, you can also send me an email at marcelo.campos@impa.br. So you can also send an email here. Okay, so now introducing today's speaker, which is Huiton Fan. He's a Clay Fellow, and he's currently in the Institute of Advanced Studies. Has many exciting results, both in probabilistic combinatorics and in additive combinatorics. Today he's talking about something which kind of mixes both, maybe more towards the additive side, and it's very exciting, so you can have it.
Thanks, Marcelo, and thanks to the organizer for putting together the school and for the invitation to the very amazing reel. Right, so let's start maybe today's story with, again, the very beginning of probabilistic combinatorics, so this amazing theorem of Edish. He showed that there exist graphs on a huge, big N number of vertices for which there's no clique or independent sets of size 2 times log base 2 of n. And I think maybe Rob yesterday already discussed this example in the probabilistic method course. So let's just quickly glance through what happens here. So in this proof, we introduced the Edish-Renyi random graph, GNP, which already appeared in many of the talks yesterday. So this random graph is a random graph on n vertices, where between every pair of vertices, we flip an independent coin, and we put an edge with probability p. So for this theorem, we will consider the random graph Gn1/2. And in fact, this is just a uniformly random graph among all of the possible graphs on big N vertices. And what Edish does is he simply considers what I will call a naive first moment or expectation obstruction. So in particular, he computes what is the expected number of cliques or independent sets in Gn1/2 of this specific size 2 log n, show that this number is very small, and hence we conclude that actually most graphs on big N vertices do not have any clique or independent set of size 2 log n. Okay? Now, in the sparse case of the Edish-Renyi random graph, when p tends to 0 as an appropriate function of the number of vertices n, the independence number of the random graph GNP has been extensively studied, and we do know very precise asymptotics for the independence number in GNP, dating back to the results of Matula, Bolobosh and Edish, and Fries, and there are other follow-ups as well. So this story in the Edish-Renyi case is fairly complete. So in today's talk, we'll turn to a very different ensemble of random graphs. That's the ensemble of random Cayley graphs, which I will introduce to you shortly. And this ensemble of random graphs is, in a sense, a very structured and highly dependent ensemble of random graphs, which makes it a lot more challenging to analyze compared to the Edish-Renyi case. Still, you will find that most of this talk is about the first moment method. So we'll try to understand the first moment obstructions in random Cayley graphs. And while this does not come up explicitly in this talk, and we'll only see briefly a glimpse of this later on towards the end of the talk, let me maybe quickly justify our interest and obsession in studying first moment obstructions, not only for this problem, but for many other problems as well. So we do know that these first moment obstructions, as simple as they are, they act as a very fundamental driving force, and they essentially dictate when structures start to emerge in very general random discrete systems. This is the content of the Kahn-Calaillet conjecture. But for us today, in the random Cayley graph case, the first moment obstructions we will see is very intimately tied to questions in additive combinatorics. But perhaps more interestingly, we do not just go to additive combinatorics and derive the results that we need to apply to the random Cayley graph. We actually devise a new purely combinatorial approach to tackle these questions of an additive combinatorial flavor. And this perspective turns out to be quite useful. We'll see it many, many times in this talk. And it actually do not just allow us to get results that we need for analyzing the random Cayley graphs. We can even go back to questions that are inside additive combinatorics themselves and resolve these questions based on this perspective. So I hope that this perspective is kind of the main message that I can convey to you in this talk, and hopefully you can also find other interesting uses for this type of a perspective. Okay, so with that, this is the rough plan for the talk. I'll start with the dense regime of the random Cayley graph, and this will have lots of connections to Ramsey theory. Then we'll move briefly away from the world of random graphs, and I'll discuss one application in additive combinatorics. This is completely deterministic. In particular, I'll tell you about Rouja's conjecture on sets with small doubling. And in the end, towards the end of the talk, we'll go to the very interesting things that happen when we send the density of the random Cayley graph to 0. Okay, let's start with the dense setup. So let me begin with the most important definition in this talk. We'll define the ensemble of random Cayley graphs. So for us, when I talk about a Cayley graph, I will fix a finite group G. And in this group G, if we are given a symmetric subset S, which just means that if an element X is in S, then X inverse must also be in S. We can then define the Cayley graph with generating set S. This is a graph where the vertices are identified with the group elements G, and two vertices X and Y are connected if X times Y inverse is an element of the generating set S. And you can check that the symmetry constraint that we impose on the generating set S is just there to ensure that this definition makes sense as an undirected graph. So for example, we can consider the group G, which is Z mod 5. And if we check S, in this case, to be the set consisting of the elements -1 and 1, which is symmetric, then the Cayley graph GS will be exactly just a 5 cycle. So now there's a very natural distribution that we can endow on the space of Cayley graphs of a group G. So in particular, we only need to specify a random symmetric generating set S, and we'll do it in the most natural way possible. So given a density parameter P, we'll define the random Cayley graph. We'll denote it GP as the Cayley graph with the random generating set S, where we include each set of elements GG inverse independently in the generating set with probability P. Okay, so maybe some very quick motivations for why we care about looking into these random Cayley graphs at all. So part of the motivation at the beginning of this talk will be towards Ramsey's theory. So first, the ensemble of random Cayley graphs is an ensemble of random graphs with a lot less randomness than the ensemble of Edish-Renyi random graphs. So perhaps it would be interesting, maybe towards the task of constructing Ramsey graphs, if we can already show that with this ensemble with much less randomness, we can already construct good Ramsey graphs. Well, a second motivation is that actually all of the small explicit Ramsey graphs that we know turn out to be Cayley graphs. In fact, there was a more special type. There are Paley graphs, which is not important for us to know what the Paley graphs are. But Paley graphs have been extensively studied, and it's a very challenging object to understand in both combinatorics and number theory. So perhaps before we try to understand fully the Paley graphs, which is a hard number theory problem, we can first try to see if we can understand their random analog, which in this case I'm taking to be the random Cayley graph. But beyond this, beyond the Ramsey theoretic perspective, random Cayley graphs and Cayley graphs, they appear in many places in theoretical computer science, number theory, group theory, coding theory, and so on. So there are lots of motivations for what we are looking at today. So with that, since the first part will center around Ramsey theory, let me introduce one useful terminology. So given a graph on big N vertices, we'll say that it is C Ramsey if it has no clique or independent set of size C times log base 2 of N. And we'll say that a graph is Ramsey if it is C Ramsey for some absolute constant C. Okay, so we can rephrase in this language the theorem of Edish at the beginning of the talk as saying that almost all graphs on N vertices are going to be 2 Ramsey. And perhaps quite unfortunately the case, even though almost all graphs are very good Ramsey graphs, there's an outstanding open problem of Edish to construct a C Ramsey graph for any constant C that still stands open. So as I mentioned before, maybe towards partly motivated by that goal, let's try to see if these random Cayley graphs, which require much less coil flips than the Edish-Renyi random graph, will give us good Ramsey graphs or not. So in particular, we will ask, what is the size of the largest independent set in a random Cayley graph GP? And let's note that if you take the parameter P to be 1/2, then again, what you are doing is just among all of the Cayley graphs in the group G, we are picking out one uniformly at random. And in G1/2, the distribution of the cliques and the independent sets are perfectly symmetric. So whatever we prove for the independent set or the independence number in G of 1/2, we'll also obtain the same conclusion for the clique number. So then we can hopefully answer this question, which is whether G1/2 is Ramsey or not. Okay, let me also mention there's a beautiful conjecture of Alon, and it says that for every finite group G, there should exist a Cayley graph in that group, which is C Ramsey, and here C is some absolute constant that's independent of the group. Okay, so maybe with that as our main motivating questions for the first part of the talk, let's see what are the results that we know regarding the independence number of random Cayley graphs. Okay, so now from the theorems on this slide, I'll just be focusing on the case P is equal to 1/2, so uniformly random Cayley graph. So the first is a very nice result of Noga from 95. He proved that the independence number of a uniformly random Cayley graph in any group G will be of order at most log n squared, where n is the size of the group with high probability. So it's well, quite close to being Ramsey, but still it's a kind of a quadratic off from the Ramsey property that we want. And up until recently, this is the best result that we know that holds in a general group G. The only more precise results that we know take place in nice family of abelian groups. So in the prime cyclic group Zn, there was an earlier result of Ben Green, and then Ben Green and Rob Morris later sharpened this result, and they prove in particular that in the uniformly random Cayley graph of Zn, the independence number is going to be asymptotically the same as the independence number of an Eddy-Schwenyi random graph Gn 1/2 with high probability. So in particular, in this case, the uniformly random Cayley graph is going to be very good Ramsey graph. And the only other case where we know a precise result is the case of the finite field vector space, Fp to the d. So here I am fixing p as a constant, and I'm letting d grow to infinity. That's the regime that I'm thinking of for this asymptotic. So for fixed p and growing d, in the finite field vector space Fp to the d, a uniformly random Cayley graph will have the independence number that is of order theta of log n with high probability. So in particular, unfortunately, a uniformly random Cayley graph already for this very simple group will fail to be Ramsey, even though it only mildly fails to be Ramsey by this log factor, but it will not have independence and clique number of order log n. And it's quite interesting if Alon's conjecture is true, which tells us that in these groups we should still expect to be able to construct Cayley graphs that are Ramsey, and yet a uniformly random choice fails. And it's, if we are equipped with the usual kind of way that we proceed in Ramsey theory, this seems to be a very intricate situation, but we'll get back briefly to this mystery later on in the talk. Okay, with that, let me state the first main reason that I want to say. So this in joint work with David Conlon, Jacob Fox, and Liana Yepremian. So we prove that, in fact, in every group G, doesn't have to be abelian, if you take a uniformly random Cayley graph, this independence number is going to be of order at most big O of log n with high probability. So in particular, you already see that this is kind of the best upper bound that we can impose in general without further information about the group. So this upper bound is particularly tight for the finite field vector spaces. Okay, and it gets very close to the log n bound. So let me say briefly how we would try to prove this theorem. As I mentioned before, we'll try to go by the first moment method. So let's try to compute what we want in the first moment method, which is the expected number of independent sets of some specific size t, think about t as a big constant times log n times log n, in the random Cayley graph GP. And here you can think that p is equal to 1/2 for this discussion. Okay, so of course by linearity of expectation, we can just rewrite this expected number in terms of a sum over all of the subsets A in the group G with size t, the probability that A would be realized as an independent set in GP. And the claim is that now that quantity will be something that looks like 1 minus p to a power that is up within some absolute constant of the size of the product set A times A inverse. So here, A times A inverse is just the set of all elements of the form A times B inverse, where A and B are elements of our set A. And to see this, this formula here, we can just very quickly check that A is an independent set in our Cayley graph GS if and only if this product set A times A inverse, okay, minus the identity element of the group, is a subset of the complement of the random generating set S. And given that, and the distribution of our random generating set, we can see very quickly that the probability of a set being an independent set should be something that looks like that, 1 minus p to the power a times a inverse. Okay, so the only annoying thing here is that there's kind of a factor of 2 because every time we pick an element to be in the generating set S, we also have to pick its inverse. But you can safely ignore that for this talk. Okay, so in particular, in proving this theorem, the main step is the following bound. So we prove that in every group G, the number of subsets A of size T, and for which this product set A times A inverse is small, let's say bounded above by K times T, this is upper bounded by the quantity here. So this quantity maybe, let's not focus too much on what it is precisely, but the point is that this bound here is tight. All of the terms in this bound are tight up to the absolute constant C. And by the union bound, you can quickly see that if we are given this bound, then we can easily show that the independence number of a uniformly random Cayley graph is at most order log n times log n. Okay, so now let's look at what this statement is about. You can see that this statement is pretty much, it has nothing random in it, and it is pretty much a statement that is very much of an additive combinatorial flavor. So in particular, in additive combinatorics, we are very much interested in saying that sets A with small product set A times A inverse have to be very special, have to be very structured. And here we are kind of saying that they are special and structured in a statistical sense, that there are very few of these sets. Okay? Now, given that perspective, okay, here comes maybe a surprise. Our proof of this theorem is entirely combinatorial, and in this proof, we will mostly forget about the group structure that's involved in the problem. So let me now tell you how that works. And in particular, now and several times later in this talk, we'll see a very interesting back and forth between the additive combinatorial phenomena and perspective and kind of how we can tackle them with purely combinatorial and random graph type of analysis arguments. Okay, so let me introduce to you our combinatorial view on the Cayley graphs. So given a group G, we can think about this group in the following combinatorial way. So let's take this group G of size of order n. Let's consider a complete graph now on n vertices, where the vertices are identified with the group element. And now we will endow on this complete graph a coloring, an edge coloring. We'll color an edge between two elements x and y with the color that is given by this equivalence class, xy inverse, yx inverse. So for example, if we have that the group G is equal to Z5, then we'll get here a complete graph on 5 vertices, and the edge coloring will be exactly the union of 2 5 cycles on these 5 vertices. So we have 2 color classes, and each of them is a 5 cycle. Maybe let's try another example. If the group G is F2 squared, then here we have 4 vertices, and the edge coloring that we will see on the complete graph, on these 4 vertices in this case, will be consisting of 3 color classes forming 3 perfect matchings. Okay? So in these 2 cases, and in general, you can see that in any such coloring that we construct out of a group G, each of the color classes is going to be 1 or 2 regular. So in particular, the maximum degree of all of the color classes are going to be bounded. Okay, so now let me try to translate all of the objects that have appeared before in this talk in terms of only these, in terms of the language of this complete graph and the edge coloring. Okay, so let's start with the Cayley graph. Now a Cayley graph on a group G is simply the edge union of some of the color classes that we have in this picture. In particular, a random Cayley graph is just a union of a few of these random color classes. We also discuss sets A inside a group with a small product set A times A inverse, and we can also perfectly translate that notion into this combinatorial picture. So a set A with A times A inverse having size at most m, this would correspond to a vertex subset of this complete graph, where within this vertex subset, the total number of colors that we see is at most m. Okay? So given this, we have been able to at least refer only to this combinatorial picture of the edge coloring on the complete graph to recover all of the notions that we have discussed before in this talk. Perhaps a surprise here is that for all of the results that we stated earlier, just remember that we have a complete graph together with an edge coloring where the maximum degree of each color class is bounded is sufficient. So at this point, we'll only keep this picture where we have a complete graph together with an arbitrary edge coloring where the maximum degree of each color class is bounded. And from now, we will completely forget about the structure of the group. Okay, so this naturally leads us to studying the following combinatorial generalization of the random Cayley graph ensemble. So let's consider a complete graph on big N vertices together with an arbitrary edge coloring C will impose the constraint that the maximum degree of each color class is bounded above by delta. We'll call this a delta bounded edge coloring. Given this, we'll say that an entangled graph is the edge union of some of the color classes. And a random entangled graph, which we call GC of P, is simply a random graph that we obtain by including each of the color classes independently with probability P. Okay, so you can quickly see that this is a random ensemble that generalizes the ensemble of random Cayley graphs. But it also includes some further examples like a random Latin square graph, but it's not important for us to know what it is today. So, as I mentioned, all of the results that we stated earlier hold true in this general setup. So in particular, given a delta bounded edge coloring on a complete graph Kn, we can count the number of vertex subsets that determine few colors, and the count will be exactly the same, roughly the same, up to a factor of delta, as the bound that we saw before for counting the number of subsets with small product sets inside a group. And in particular, by the same first moment method, we can conclude that, in fact, for these random entangled graph, the independence number is of order log n log n with high probability. Okay. So I want to say a little bit more about how we can prove this result, about counting subsets that determine few colors. This will motivate us to discuss what I will call the main combinatorial lemma, and that is the main lemma that will run through the rest of the talk. It will derive many other corollaries out of that main lemma. So to prove this counting result, it turns out that the main step is a purely structural statement about what we can find if we are given a vertex subset of size t together with a proper edge coloring on this vertex subset that uses few colors, let's say k times t many colors. Okay, so here, let me clarify the setup. We have a graph on t vertices together with a proper edge coloring, and this proper edge coloring uses k times t many colors. And the structure that we will be able to find, given only these conditions, is that we'll be able to find a tree that cover many of the vertices, almost all of the vertices of the graph. And this tree uses relatively few colors. It uses at most big O of k plus log t, many colors. Okay, so we quickly remark that this result is optimal. And in fact, if you want a bound of the form k plus log t, then we must have some positive epsilon fraction of the vertices that we cannot cover. Okay, so this lemma, in turn, is a corollary of the following combinatorial lemma that I will introduce to you now. And the statement of this lemma is somewhat long, but it's very clear in a picture. So let me explain to you what it means. So first, a piece of notation. In the setup where we have a complete graph together with an edge coloring, let me denote by n of a and b, where a and b are two vertex subsets, the set of colors that appear between the two sets of vertices a and b. Okay, so this is the statement in words, but ignore it. Let's look at it in picture. Okay, so what do we have in our setup? We have a proper edge coloring on a vertex on a graph on vertex set A of size t. This edge coloring, as before, we assume that it uses at most k times t many colors. There's a small technical condition, but let's ignore that. It doesn't matter for our intuition. The conclusion that we can produce is the following combinatorial structure. We can find a small set of color S. It has size at most big O of k, independent of t, so that using only the colors in S, we can connect up these balls bi, and they will have the following three key properties. So first, most of the vertices in our set A, let's say at least A over 2 vertices of the set A, are covered in these balls bi. The second condition is that these balls bi, they can all be connected by using only the colors that come from this small set of colors S of size big O of K. So in this picture, this is the red and the green color. And the last condition, which is kind of the main point that why we derive this lemma, is the statement that for any such ball Bi, if you take any one such ball, and you take any large subset A prime of the vertices, so A prime is some constant fraction of the total number of vertices, then the number of colors that we can see between this ball Bi and the set A prime will be within a universal constant factor of the largest number of colors that we can have, which is K times T. Okay, so maybe let's quickly interpret what this statement means. So really the only assumption that we have in this lemma is that we are given a proper edge coloring on this graph A of T vertices that uses few colors, but it's a proper edge coloring. That means we have kind of a very nice local condition. From every vertex, when it looks at the environment around it, it sees distinct colors. That's a nice condition that we have around every vertex, but it's a local condition. And what this lemma is doing is kind of amplifying that local condition by a factor of K, roughly. We're saying that we can build these balls, they will be roughly of size K, and around each of these balls, we can amplify the nice local condition around a vertex by a factor of K. And that's why it's very useful. You can also think that it's kind of finding these very good connected components that kind of broadcast information and talks to other parts in the graph in a very nice way. Okay, so maybe to give a sense of why this is useful, let's very quickly see how we can derive the lemma that we have earlier. So this lemma here, that in any such proper edge coloring using few colors, we can find a tree, connect up a large set of the vertices using relatively few colors. Let's see that this is a quick corollary of the main combinatorial lemma. So in particular, let's first apply this combinatorial lemma. Let's throw away all of the vertices of A that are irrelevant, and let's just focus on this part of the vertices that lie in the balls Bi. So here I have only used K colors to connect up these balls. Now in every step, let's expose a random color from the original set of K times T many colors. Because of this third condition on the balls Bi, for every random color that we expose, with a constant probability, each of these balls will connect to some other ball. You can use that to show that the expected number of connected components that we have, every step that we expose one random color, that should go down by some constant factor. So in log T many steps, we will be able to merge all of these balls to one single connected component, and that's exactly what we want in the structural lemma. Okay, so this is the first use of the combinatorial lemma. Any questions regarding this picture? Yes?
Before you wanted to cover 1 minus epsilon fraction.
Yeah, that's right. So doesn't matter, I keep cheating, but yeah, so you can change this half to any 1 minus epsilon. And for some applications, it's important to know what is the quantitative trade-off, but for this one, it doesn't matter. Good. Cool. Right. If there's no, oh, yeah.
What's the construction? Sorry, Michelle? What's the construction?
Right, so this construction is not long, but it's actually somewhat tricky. So it's, again, a random exposure of colors, but what's tricky is that you can't only kind of, what we hope to do is maybe around every vertex we expose random colors and build connected components, and it will be nice if we can always just kind of look towards the future. So we'll only use future colors in order to grow the components. Turns out it doesn't work for proving this, so we have to do very careful conditioning. We kind of grow the components, but sometimes we may use colors that have already appeared in the past. So making all of that work carefully is kind of the, but it's a random exposure and growing component type of argument. Okay. Right, so with that, I will maybe very briefly address this mystery, perhaps, if you are interested in Ramsey theory, of addressing Alon's conjecture. So in Alon's conjecture, he asked to show that every finite group has a Cayley graph, which is Ramsey. But even for the very simple groups, let's say F5 to the D, we saw that a uniformly random Cayley graph will fail to be Ramsey. So how on earth can we find a Ramsey Cayley graph for these groups? Okay, so it turns out that it's not the end of the world. So we can look a little bit closer, and we can figure out that the uniformly random Cayley graphs, they are not Ramsey for, in fact, a very good reason, good and simple reason. So in fact, the large independent sets and cliques that appear in a uniformly random Cayley graph over F5 to the D, they are exactly just subspaces or subgroups of an appropriate size, so they have a very simple structure. Okay, in fact, you can easily show this just using the second moment method. We can show that if we take a random subset of F5 to the D, then we will be able to collect all of the non-zero elements of some subspace of order asymptotically larger than log n. Okay, but well, subspaces are very simple, so perhaps we can try to just slightly modify the construction to remove all of these problematic, large, spurious, large independent sets. And that is indeed possible. So in work with David, Jacob, and Liana, we proved that over these groups, finite field vector spaces Fp to the D with a catch, P have to be at least 5. There exist Cayley graphs with clique and independence number matching the Edish-Renyi number. So 2 plus zeta of 1 times log base 2 of the size of the group. And in fact, we can show that for almost all n, all abelian groups of order n will admit a Cayley graph, which is C-Ramsey, so addressing Alon's conjecture for all of these cases. And there's nothing mysterious about this almost all. We have trouble in characteristic 2 and 3, so as long as n is not dominated by powers of 2 and 3, we are okay. Right? So let me tell you how to modify the ensemble of random Cayley graphs in order to find these Ramsey Cayley graphs. Okay, let's ignore this adjective self-complementary. Alon and Orlowski asked for it, so we added that adjective, but for this talk, it doesn't matter. So this is our construction of this modified distribution of random Cayley graph that will produce successfully a Ramsey graph. So in F5 to the D, let's say, for concreteness, we can look at all of the non-zero directions. So let's look at all of the lines in F5 to the D. So each of these lines we can partition into 2 equivalence classes, right? So x minus x, which is 4x, and 2x and minus 2x, which is 3x. In a uniformly random Cayley graph, we would have chosen each one of these equivalence classes to be in the generating set independently at random. But in this case, we'll introduce this correlation. So in this model, we will just randomly pick exactly one of these 2 generating sets to be, exactly one of these 2 equivalence classes to be in our generating set. And the other one will force it to be outside the generating set. Okay, so immediately, you can see that if we pick a random Cayley graph from this model, then no subspace, no non-empty subspace, have any chance of being a clique or an independent set. So hopefully, that has removed many of the problematic large cliques or independent sets in a uniformly random Cayley graph. And indeed, we can show that it removes all of the spurious problematic cliques and independent sets. So let's just focus here on this third, which is the simple but most important property of this construction, which is that whenever we have an element x, which is in the generating set S, then 2x must be outside of the generating set S. And we did this exactly to force all of the subspaces to be impossible to be an independent set in this model. But more generally, we can use some additive combinatorics, Plunacher-Rougeo's inequality, to show that in fact for any set A with a positive chance of being an independent set or a clique, we must have that A have very large doubling. So the size of A minus A must be at least A to the 4/3. Okay, so here we are in an abelian group, so that's why instead of writing A times A inverse, as we have seen before, I'm writing it as A minus A. But it's the same as the AA inverse that we have seen earlier. Okay, in particular, once we are given this, combined with the counting result that we have previously, we can derive the Ramsey property of a random Cayley graph that we draw from this random model. Now, I claimed a sharper result. I claimed that we can get this sharp 2 plus liter of 1 times log base 2 of n bound on the independence and the clique number. And for this, we'll combine the previous argument, but there's one further input that we will need, which turns out to relate to Rougeo's conjecture over F5 to the D. So it's kind of a good turning point that I will next turn briefly to this application in additive combinatorics that's around Rougeo's conjecture. Okay, and I turn the page. All right, so well, already many times in this talk, we have seen that the kind of main question that we are motivated to study are kind of questions that ask us to understand the structure of sets with small doubling. So let's say sets with small product set A times A inverse in some group. So for these results, let's go back to classical additive combinatorics. So let's just work with an abelian group G. And in fact, it's more convenient now to talk about a sum set instead of a different set. This is a collection of all sums A plus B, where A and B are elements of A. And let me denote the doubling K which is the ratio between the size of the sum set A plus A and the size of the set A. So if you have seen additive combinatorics before, then you know that a very major theme in additive combinatorics is to associate to sets with small doubling K some notion, some explicit or implicit notion of additive structure on a set A. And a classical example of this is Feynman's theorem. So for this, we are taking our group as the group of integers. So here's not finite, but it's OK. So for a set A of integers, it's easy to show that the sum set A plus A must have size at least about twice the size of A. And equality here will only be attained if A is extremely structured, if A is an arithmetic progression. On the other end, if A is very unstructured, then the sum set can be as large as roughly quadratic in the size of A. So there are more examples of sets with small doubling that you can construct. So for instance, we can take the so-called generalized arithmetic progression, or GAP. So here's the formula of a generalized arithmetic progression. Let's not worry too much about what it is exactly. You can just think about taking a box in D dimension, in ZD, and then taking an appropriate linear projection of this box back to the integer line. Okay? Since if you add a box to itself in D dimension, the volume can grow by at most a factor of 2 to the D. You can show that after you do the projection to get the gap, it will also have doubling, which is bounded, as long as D is bounded. And in general, if you want to construct a general set with small doubling, you can also take dense subsets of these generalized arithmetic progressions. Right, so of course, we can ask, oh, are these all of the sets that have small doubling in the integers? And the phenomenal result of Feynman tell us that the answer is indeed yes, at least qualitatively. So we show that for every set, A of integers with small doubling K, A must be a dense subset of a generalized arithmetic progression B that have bounded dimension. Okay, so all of these bound are implicit constants that depend only on the doubling K. Well, given this qualitative result, it's been an important theme in additive combinatorics to understand quantitative aspects of Feynman's theorem. So what are the dependencies of this dimension and the density of A inside the gap P in terms of the doubling K? But for us today, we'll not be interested in this infinite group Z. We'll be working with an even nicer setting, which is finite abelian groups with bounded exponent. Okay? An abelian group G will say have exponent R if R is the smallest integer that divides the order of every element of the group G. So for us, we can always just think about the canonical example of an abelian group with exponent R, which is the group ZR to the D. Okay. So again, in this general finite group setup, we can ask, okay, how large can the size of the sum set A plus A be? And again, it's between roughly A and quadratic in A. It is very small, let's say the size of A, only if A is extremely structured, only if A is a subgroup of G. And we can ask, what about some slightly larger K? What are the sets A inside the group G with a bounded doubling K in general? Ruja, in 1999, proved an analog of Feynman's theorem over these abelian groups. So he showed that if G is an abelian group with exponent R and A have bounded doubling K, then A must be a dense subset of a subgroup of G. Okay, so an even cleaner characterization than in Feynman's theorem. And again, we are interested in understanding what is the correct quantitative dependency here. So in particular, in his paper, Ruja posed a conjecture that if we take an abelian group G of exponent R, and if we have a subset of doubling K, then A must be contained inside a subgroup of size at most R to the big O of K times the size of A. And while he didn't just arbitrarily put out this upper bound in the conjecture, it turns out that it's very easy to construct examples showing that in the worst case, we need the size of the subgroup H containing A to be at least something like R to the 2K times the size of A. So we need some exponential dependence here. And there have been quite a few works over the years on Ruja's conjecture. In his original paper, he shows a bound of roughly R to the K to the 4 between the size of the subgroup H and the size of A. And Green and Ruja improve it to R to the K squared, roughly. And in the breakthrough on the quasi-polynomial Bogoliub of Ruja's lemma, Sanders showed that we can get a bound of roughly R to the K times polylog K. Well, this is the best result that we know for a general abelian group with bounded exponent. The only cases when we know better results are when the abelian group have prime exponent. So if we are in the case where the group G is a finite field vector space, then we know sharper results. So in this case, we first have the theorem of Green-Tao, which resolves Rougeat's conjecture for F2 to the D, and then it was later sharpened by Eben-Zohar and Lovett, in particular, getting the sharp bound on Rougeat's conjecture for all of the finite field vector spaces, Fp to the D. Okay, but in principle, I think even for prime power, Fq to the D, Rougeat's conjecture is not known. So let me maybe, you saw that there are two sets of different results in the previous one. So one applies to general abelian groups, and that follows kind of more traditional additive combinatorial and analytic technique, uses some Fourier analysis. And it's very good at working with general abelian groups, but there's a catch, which is that it seems kind of challenging to completely remove some of the small factor, the polylog factor, out of Sanders' result. On the other hand, we have the other set of results which are very sharp over finite field vector spaces, and all of these are derived with completely combinatorial arguments. So the result of Green and Tao and of Eben-Zohar and Lovett, they use local modifications or compressions, but these crucially only work when you have the very nice vector space structure and immediately breaks when we don't have a vector space Fp to the D. Okay, and there are indeed cases where groups with composite exponent behave significantly differently from a group with prime exponent, especially for these type of arguments. So we may ask if, okay, this is a worrying sign that whether Rougeat's conjecture is true for general abelian groups of bounded torsion or not. Well, okay, in joint work with Jacob Fox, we proved that Rougeat's conjecture indeed holds, and we proved the following strong form. So we show that if A have doubling at most K in the group of exponent R, then it must be contained in a subgroup of size roughly R to the 2K times the size of A. So this is sharp up to the little o of 1 next to this exponent 2. Okay. And let me briefly tell you how we prove this. The main tool you are already familiar with. So the main heavy lifting step is to apply the combinatorial lemma. And I'll tell you what it gives in this case in a second. But then there is a second step in proving this conjecture, which is we need to combine this combinatorial structure with some further additive combinatorial ideas. And what we achieve out of this step is essentially reducing the problem from working with a set with doubling K, which is a general parameter that we want to understand the quantitative dependence on, to another set that has doubling, which is now an absolute constant, which you don't care at all about the quantitative dependence. Okay, so it's kind of a way to reduce the quantitative results to a qualitative result. So let's see briefly how it works. So first we apply the combinatorial lemma. Okay, maybe let me just say what it gives you. This is an easy translation between the two setups. It will give you a subspace H. It is spanned by few colors, big O of K, sorry. It is spanned by few group elements, big O of K many elements. So you can think about this H exactly as the span of the few color set S that we found earlier in the combinatorial lemma. Okay, this subspace H will have the further property as follows. It will partition most of the set A into sets AI. So each of these AI is the intersection of A and a coset of the subspace H. And we have this nice property that for any such intersection AI, for every large subset A prime of A, the size of the sum set A prime plus AI will be a universal constant factor of the largest that it could be, which is the size of the total sum set A plus A. Once we are given this, what we apply on top of it is a very nice recent direction in additive combinatorics. So it's a recently discovered phenomenon by Bolobash, Lieder, and Tiba. And the phenomenon can roughly be summarized as saying that large subsets can often be realized by using only small subsets. So in particular, in the original paper, Bolobash, Lieder, and Tiba showed that, well, for subsets of ZP, we have the Cauchy-Davenport inequality saying that the size of the sum set A plus B must be at least the size of A plus the size of B minus 1. And in fact, they prove that we don't need to use the entire set A in order to prove this inequality. We can already saturate the inequality by picking only a constant number of elements out of the set A. Okay, in my later work with Jacob, Sami, and Yunkun, we actually show that it suffices to take here just 3 elements, which is correct bound. But the exact version that we will need for Rougeat's conjecture is a slight variant of this phenomenon. So in my work with Jacob Fox, Sami Luo, and Yunkun Zhou, we show that in a general abelian group G, if you have a set A with large doubling, so let's say A plus A is at least some parameter lambda times the size of A, then you can find a large subset, A prime of A. A prime will have size at least lambda to the 1/3. So in particular, if lambda grows to infinity, the size of A prime we can take to grow also to infinity. And it will have the property that the sum set of A and A prime is within a universal constant factor of the trivial bound, which is the product of the size of A and the size of A prime. Okay, so given this result, what we can prove is roughly that we can combine the output of step 1 and this theorem to show that we can take a suitable subset A tilde of A, and after we quotient it by the subspace H, we will now obtain a set whose doubling is a universal constant. Okay, so this big O has no dependence on the parameter K, and then we apply whatever qualitative result that we want on this quotient A tilde mod H, and it is easy to see that we can go back from the structure of A tilde mod H to the desired conclusion that we want on the set A.
I didn't understand this step. Yeah, just this last step.
So last step, how to go from here to here?
Yeah, how to go from this theorem to the...
Right, so roughly the picture is as follows. So we produce a few of these cosets of H. Each of them have one of the set AI. And each of these AI in turn have the nice property that no matter what large subset of A, the sum set of AI and that subset of A have doubling at least K times the size of A, where K is the doubling of A, okay, up to a universal constant factor. Now, for this quotient, let's assume that the sum set of the quotient have doubling going to infinity. You can apply this theorem here to show that you can iteratively select some growing number of cosets here, each of them producing a large sum set with the remaining part of the set A in a way that you can make sure that all of them are disjoint. And in particular, if there are a growing number of these, then you can get that the size of the sum set A plus A is at least the number of cosets that you can pick multiplied by this universal constant factor times the size of A plus A. And this is a contradiction. Okay, so that's roughly how it works. Okay, so any other quick question around this? All right, so if not, then allow me to return to random graphs. So I promised that in the last part, I will just briefly tell you about what other interesting things would happen if we try to go from the dense random Cayley graph to sparse random Cayley graphs. And in this case, we'll not only need additive combinatorics, we'll need further probabilistic ideas. So I hope that there's some interesting message here. And again, there will be some nice connections to a question in additive combinatorics. Okay, so what's the sparse regime? Well, simply sending P to 0 as some appropriate function of the size of our group G. And this case is challenging enough. Let's just focus on the case of an abelian group G. You can, in fact, just even think about G as a cyclic group, Z mod n for a prime n. Okay, so the first point here that we observe is that maybe one of the key challenges in analyzing sparse random Cayley graphs is that the naive first moment that we have discussed earlier, the expected number of independent sets of size T in this sparse random Cayley graph GP will always be too large, no matter how slow P goes to 0. So in particular, you can easily show that even over a very nice group like Zn, the number of subsets A of size T and an absolute constant doubling, let's say 10, will always be exponentially large in T. For example, you can take any subset of size T of an interval of length 5T. And you can check that already just from these sets, they will contribute a quantity that is way too large to the naive first moment. But of course, I introduced the adjective naive for a reason, so we can try to remove the word naive, and we can move to a more honest first moment obstruction. And this is the description of what is a more honest first moment obstruction, which will be our goal to construct for the rest of the talk. So in particular, in general, what we want to find to get general first moment obstruction is the following. So let's say that you have some collection H of subsets here of a group G. So think about this collection as the collection of all of the sets A minus A, where A have size T. This is the collection of sets that we care about. This is the collection of sets that we want our random sample to not hit, right? So we don't want the random sample to contain fully any set from this collection. Now, we will say that a family G of subsets of the group is a cover for H if every set from the collection script H contains a set from the collection script G. So maybe not the exact example that we're interested in, but one that's easy to keep in mind. You can think about this family H as all configurations in the group that is formed by a 4-term arithmetic progression and some other 3-term arithmetic progression in the group. Oops. In this case, you can take, for instance, a cover G of H, which consists of all 4-term arithmetic progressions in the group. And you can see that every configuration in H must contain at least a configuration in G. So by this definition, G would form a cover for H. Okay. And in fact, this is a case where there's a good reason to move to this cover for the family H. Okay, now we'll call a first moment obstruction, or exactly a cover G of the family H that have this small union bound proxy. So call this a union bound proxy, or you can call it a cost. It is just a sum over all of the sets in the cover G of, in our case, 1 minus p raised to the size of the set G. Okay, I just realized it's a bit of a bad notation. This G is not a group, it means a subset of the group that lies in our cover script G. Okay, so once we can find a cover with a small cost this way, then just simply by the union bound, we can certify that it must be likely the case that a random subset of G does not contain any of the sets from H. And the sets that we care about, again, are the sets of the form A minus A, where A have size T. Okay, so now our goal will become kind of how can we construct an efficient cover, so a cover G of small cost for this specific collection of sets. Okay, maybe before that, let me tell you about some of the results we know regarding the independence number of sparse random Cayley graphs. So first, there's a very beautiful theorem of Noga alone. It showed the following two bounds on the independence number. So the first bound is roughly square root n over p, and the second bound is roughly p to the minus 2. The first bound, which you can guess, comes from spectral graph theory. So an old theorem of Alon and Reuschmann shows that the random Cayley graphs will be very good spectral expanders. So in particular, all of the non-trivial eigenvalues are around square root of the degree. And you can combine that with Huffman's bound to derive the first upper bound on the independence number. Now, this first upper bound is not very good. In fact, it's very bad in the range where the density p is not going to 0 very fast. So for example, you can take p to be a constant, and this first upper bound will only give us something like root n, where we expect something that is of order log n. So indeed, for p that is not going to 0 too fast, the second bound, which is roughly of order p to the minus 2, will be a better bound, and this bound in turn follows from a simple construction of a small cover for the collection of sets A minus A. Okay. Now, what do we expect to be the truth? There's a conjecture of Noga, and he conjectures that the independence number of GP is of order big O tilde of P inverse. And there's a good reason to conjecture this. For instance, a random Cayley graph is a random graph where it's regular with degree roughly n times p. So perhaps if things are nice, the independence number of a random Cayley graph should behave similarly to the independence number of a random n times p regular graph. And in that case, we will have this bound of roughly p to the minus 1 for the independence number. Okay. I want to briefly get to this connection to additive combinatorics. So allow me to introduce a slight variant of the model that we have been discussing. So before we talk about the Cayley graph, let me now introduce the Cayley sum graph. It's even simpler than the Cayley graph, but it only works over abelian groups. So in this case, given a abelian group G and an arbitrary set S, there's no symmetry condition, we can form the Cayley sum graph, which is again a graph on vertex set G, and we connect x and y if the sum x plus y is an element of the generating set S. And then we can similarly take a random Cayley sum graph G plus P by just selecting the elements in the random generating set S at random, each of them chosen with probability P. So it turns out that independence number of random Cayley sum graph is closely related to the following question that was first studied by Ben Green and Green and Gowers. So they ask, what is the smallest t so that every subset of the cyclic group Zn of size at least n minus t can be written as a subset B plus B. Okay, so the question makes sense. Let's call that quantity f of n, that's the smallest t, so that every set bigger than n minus t is a subset. So Noga, by leveraging connection to the independence number of sparse random Cayley graphs, proved the following bounds on the quantity f of n, and he conjectured that the correct order for f of n is n to the 1/2. So this conjecture is actually a direct corollary of the conjecture we posed earlier regarding the independence number of a sparse random Cayley graph. Okay, the connection is very neat and simple, but let me skip it. So maybe in the last 1 minute of the talk, let me say that, okay, so first, well, this is a result First result is just kind of a smooth interpolation of what happens in the sparse case and what happens in the dense case. But you can see that when p is small, the bound here is still stuck at the exponent of p to the -2. There's no improvement to the exponent. And in very recent work with Noga, we can improve the exponent from -2 to -3/2, and in turn that gives us an improved exponent for this question of green. Let me just say in one word that all that we do is to find a more efficient cover for the collection of subsets, and particularly in the case where the subset is small. And I think I will try to end here. There are some further results that we can get out of this and some further interesting connections to additive combinatorics. But all in all, I think there's lots of interesting things to look around here. So for instance, we looked at lots of problems in the study of monotone properties of Édès-Régnier random graphs, and already for kind of the simplest monotone property that we can find, the problem is already very challenging for the random Cayley graphs. So perhaps it will be, it will be interesting to see what we can do regarding interesting monotone properties in random Cayley graphs. And there's this other problem regarding Alon's conjecture that's related to Ramsey theory that I posted yesterday in the open problem session. But here, it seems that the obstruction to finding a good Ramsey-Cayley graph in F2 is just to really find a corollary of F2 that allows us to avoid monochromatic subspaces. And we don't really know how to do that. So, let me end here. Thank you.